In this lecture, we're going to talk about polyprotic acids. Polyprotic means multiple protons, and polyprotic acids are just acids that have more than one acidic hydrogen. Here's an example of one, sulfuric acid. Sulfuric acid is one of our strong acids that we assume dissociates completely or ionizes completely. Looking at sulfuric acid, which is H2SO4, it has these two acidic hydrogens right here. So we're looking at these ones right here. And they're equivalent. They are both bonded to an oxygen that's bonded to a sulfur, that's then bonded to two other oxygens with double bonds, and then another oxygen with a hydrogen. And so these are exactly the same and equally likely to ionize and to have that oxygen-hydrogen bond break. But once that happens, then the molecule becomes very different. So if we put sulfuric acid in some water, we'll have one of those hydrogens removed rather than both right away. This is going to go stepwise because once we remove one, we're dealing with a fundamentally different molecule. So HSO4 here, and I've drawn it out for you. It has an overall -1 charge, right? And it still has an acidic hydrogen right here. So we still have one of our acidic hydrogens. But that acidic hydrogen is now part of an anion rather than a neutral molecule. To lose that hydrogen, to ionize, this will now go from a -1 molecule to a -2 molecule. And that's very different. That's an accumulation of a magnitude of charge that's significantly larger. And there's the maintaining something that has a large magnitude of charge is less stable than something that's neutral. And so it's less likely that this hydrogen that's left will ionize than the first one when we compare the two. And so it's not going to have the same equilibrium constant for its acid dissociation for that hydrogen. And so they're going to be different. So when we look at the next step in this polyprotic acid, which is this HSO4 minus reacting as a base with water to SO4 minus 2. So when we look at HSO4 minus reacting with water as an acid to form SO4 minus 2, we can see that it's actually going to have an equilibrium constant that's not only different, but less. So this would be considered Ka2. We would have Ka1 describing our first hydrogen that is ionized from our acid. And these will be different values. And if you wanted to know what they were, you could find them experimentally. Or you can, if for well-known acids, look them up in a reference table. Now, usually the first and second Ka are so different that it's really just the first equilibrium constant that impacts that hydronium ion concentration and then the pH of the solution. And so a lot of times we'll find ourselves ignoring subsequent Ka values and just basing our calculations around the pH of a solution on the first one for polyprotic acids. And we'll go ahead and prove that to you through an example problem in a bit. An exception to this is sulfuric acid. So this is a strong acid. Its first equilibrium constant is so large that we just assume all of our sulfuric acid becomes HSO4 minus. And then that second Ka is actually pretty big too, in the relative world of Ka values. And so it'll have an impact on the overall concentration. And we'll go ahead and show that through an example problem now. First, here's a couple examples of polyprotic acids, just so you're aware of them. Sulfuric acid we just talked about. Oxalic acid is our carboxylic acid group, but two of them brought together and bonded. And then we have sulfurous acid, which is like sulfuric acid, but with one less oxygen. And phosphoric acid is one that is really common in biology. And that one's actually triprotic. So let's take a look at that sulfuric acid problem I implied. So here's sulfuric acid written up in the corner. And so we're going to have this sulfuric acid dissociate one proton, and we're going to form this HSO4. HSO4 is going to have a Ka value then when it reacts with water to form SO4 -2 of 1.2 times 10 to the -2. Now remember, just water on its own, its autoionization equilibrium is going to be 1 times 10 to the negative 7th, right? So like, or sorry, negative 10, 14th. And so like negative 2 is pretty big compared to something like that. Um, and so it's a weak acid still because K is less than 1, but it is still a pretty good sized number. It's in that range that we typically have for reactions at equilibrium. It's like about 0.01 to 100 for a K value. That says that, you have both your reactant and your product present in meaningful quantities. So to solve a problem where we're trying to determine the concentration of H3O plus, we are going to take into account both of these ionization steps. But the first one is strong. So we're actually going to assume that all of our H2SO4 converts into HSO4 minus. And so we're actually going to call that H2SO4 concentration our initial concentration for HSO4 minus. And we'll be able to solve this problem by focusing just on the second equilibrium of this polyprotic acid. So let's go ahead and start working on this. We have the concentration of hydronium ion we're going to assume is 1.5 molar initially, because that is going to be the concentration of our H2SO4. I've written out our K expression for our second equilibrium right here, reaction. And that's what we're going to focus on. So let's solve this next. It's going to take an ice table because anything with equilibrium is going to take an ice table generally. So let's rewrite this as an ice table. So we've got HSO4 minus plus water is forming SO4 2 minus plus H3O plus. We're going to assume we have a 1.5 molar concentration of our HSO4 minus. But now remember, as we looked at our first reaction, whenever we produced an equivalent of HSO4 minus, we also produced an equivalent of H3O plus. And so that initial concentration of our H2SO4 is going to be both our initial HSO4 minus and our hydronium ion concentration. And we don't have any SO4 negative 2 yet. So will I form more products or reactants to reach equilibrium? I have 1.5 molar of a reactant and also a product. And the kind of shortcut way to figure this out is to notice that I have a 0 concentration for one of my products. That means no matter what, I have to form some of that for equilibrium to be reached, since that K value is not 0, right? So that means that this reaction is going to form more products to reach equilibrium. So I'll be adding X to my product side and subtracting X from my reactant side. Now, if you weren't sure, you can figure this out by calculating Q. So Q would be equal to 0 times 1.5 divided by 1.5, which would equal 0. And that Q value then is going to be less than K, so it's going to proceed to our products. So then we'll come back to our change. We'll subtract X from our reactants. Now I have coefficients of 1, so it's just minus 1X, which I write as X. And I'll gain X on both of my products. That's going to create equilibrium concentrations of 1.5 minus X, X, and 1.5 plus X. So I'll plug that into the equilibrium expression that I had before. So we've got that given to us right here. So that Ka value is 1.2 times 10 to the negative 2. And it'll be equal then to that product X times 1.5 plus X, all divided by 1.5 minus X. And so this is going to quickly lead us to a quadratic. I can see that I'm going to have an X value. I'm going to have just a number without an X, and I'll have an X squared. As I'm solving this, I'm distributing this X first out into these parentheses, and I'm multiplying both sides by 1.5 minus X. And as I do that and start to solve, I'll be able to rearrange this into an equation that looks like 1.5, sorry, x squared plus 1.5x, sorry, 1.512x minus 0.018. And that'll all be equal to 0. And so I've been able to get all my x values on one side of the equation, but with both an x squared and an x, I need to set this up for the quadratic equation. Remember this x squared in front, this is going to be a, b, c. I'm going to plug this into my quadratic. And I get two values. I get x is equal to 0.118. And I get x is equal to negative 1.528. Only one of these makes sense, right? We can't have a negative x value for concentration. We can't have like negative molecules. And so this is the only one that's reasonable. So I plug that back into my equilibrium expressions for change, right? And the one that I'm actually really interested in only is the H3O plus. Because I need to calculate the pH, and the pH is only going to depend on that one. So I can always calculate all my equilibrium concentrations for my reactants and all my products, but I'm just going to focus on H3O plus here. So that concentration of H3O plus is equal to 1.5 plus 0.0118. And I'll be giving then, and I can then plug that into my pH equation. So pH is going to be equal to negative log of 1.5118, which is going to give me a value that is negative 0.179. I'm going to highlight that since there's a lot of work shown here. All right. So that is going to be my concentration. Let's actually go back and compare this, right? So I have from my second one, I found that if I take into account Ka2, so if we only calculate pH using Ka1, so if we just looked at that first reaction of all of our H2SO4 dissociating, we would be using that 1.5 molar. So pH would be equal to the negative log of 1.5 rather than the negative log of 1.5118. And that gives us a value that is negative 0.176. So I'm going to highlight that a different color. And so if we only use our first equation, we get pH that's actually different from if we use both for H2SO4. They're still extremely close. And if you were estimating to just like two significant figures, you would say these are both 0.18, right? Negative 0.18. But this is enough that we can say, oh, well, it was important for us to take into account that second equilibrium constant for sulfuric acid. And now this was a K value that was large relatively for a weak acid. And so if it's much smaller, then this difference is going to get smaller and smaller and smaller until it's just insignificant pretty quickly.